Uh, Good morning, everyone. I'm Kaiwei. I'm currently a master student in Southern University of Science and Technology. Today, the title of my presentation is DSCformer, a dual-branch network integrating enhanced dynamic snake convolution and SegFormer for crack segmentation. Here is the outline. I'll start with background, related work, methodology, experiment, and finally is conclusion. As we know, crack segmentation is a classic task in computer vision on construction. As buildings age, structural damage become more likely, and crack is an early warning sign. But if inspection is poor, serious accident like collapse could happen. So that's why regular inspection is essential. As for crack inspection method, manual inspection is subjective and dangerous. So the researcher turned to computer vision early on. But traditional methods like threshold suffer from low accuracy and are sensitive to noise. So the deep learning has since become mainstream approach, offering better segmentation accuracy and robustness. Existing deep learning model falls into three types. The first one is convolutional neural network. It's good at extracting local features, while transformer is good at capturing global dependencies and help with complex background. But both of them has some limitation. So the third one combine them, balance the local feature and the global feature, and is more robust. So we will follow this structure. With deep learning evolving, the convolution has many variants. Dilated convolution expands the receptive field. Deformable convolution learns to geometric deformation. And recently, a new one, Dynamic Snake Convolution, DSC for short, add a constraint to adapt the tubular or topological structure better, like this. So based on them, our goal is to build a model with stronger background filtering and finer, more accurate crack segmentation. Let me introduce our method, DSCformer. It uses a transformer and convolution encoder. Transformer branch uses a pre-trained SegFormer Bezier encoder, which has strong prior knowledge with background understanding, and the convolutional branch stacks several dynamic snake convolution blocks, extract fine-grained features with different resolution, and then fills feature maps from the dual branch encoder and perform a progressive upsampling for final prediction. We propose the enhanced dynamic snake convolution by improving in two ways. First, the computation process is below. First, we will compute the offset field by a pyramid kernel. The small one will compute the point, the offset between near the central point, and the larger one for further away. By the offset field we got, start from center point and iterate outward to form a snake-shaped path. Since the image points are discrete, we need to apply bilinear interpolation to sample the value from any point. And finally, followed by the standard convolution operation. And to fill the feature map from different branches, we proposed a weighted channel attention module. It applied a global average pooling and the global max pooling to the input feature map and generate two spatial descriptors, and followed by the independent two-layer perceptions, and then concatenate and weight them to provide a channel attention map. This improves the information fusion on different pooling layers. And to analyze what each encoder learns, we visualize the feature map. As you can see, the enhanced dynamic snake convolution has strong ability to extract edges and find structures. In contrast, SegFormer encoder provide a uniform activation and is less biased toward edges. So this shows the complementary strengths for two branches. As for experiments, we trained and validated our method by two public datasets. One is Crack3238 and another one is FIND dataset. As you can see, our method filters the background noise very well, and on large defect, the segment mask is complete, and it also provides a more accurate edge delineation with proper width. For quantitative results, we use common metrics like IoU, precision, and recall. Our method outperforms others with around 2% improvement in IoU. And we also conducted the ablation study by comparison of convolution types, and we test the impact of WCAM, and we compare the single branch and dual branch architecture. All result shows the consistent improvement, confirm the effectiveness of our method. To summarize, we propose an enhanced dynamic snake convolution and a weighted channel attention module. And based on this, we propose a hybrid model, DSCformer, for crack segmentation and outperforming the SOTA method across two public datasets. In the future, we aim to address some limitation like field 3D data and develop a lightweight version of our method. That's all. Thank you.